Okay, so we are going to revise solubility Chem 113, and this is Chem 113, and this is a very high yield area. So I just go straight to the point, and we'll look at the specific ask you. All right, so let's begin. So once you look at solubility, solubility is just the same as concentration or molarity, which we've been calculating for. So we take C. So anytime you are asked to calculate for solubility, you are basically going to calculate concentration. And we know that we can calculate concentration in two ways. We can find the molarity, or we can find the mass concentration. So when you're asked to calculate solubility, just go ahead and find your molarity. So this one will be in what? Mole per liter. And this one is going to be in what? Gram per liter. When you're asked to calculate solubility, when you just hear solubility, you are referring to. If the question says calculate solubility in gram per liter, then you can go ahead and find it in this way. And then we know the relationship between molarity and mass concentration. So we have to know how they are related. And the relationship between mass concentration and molarity is rho equals mc. So we have your molar mass here. So this is your molar mass. All you have to do is what? If you want to change from mass concentration to molarity, you just have to divide your mass concentration by your molar mass. Okay, so just take note that molarity liters is the same as dm cube, and then milliliters is the same as cm cube. Most students get confused with this, so just take note. This is the difference. Okay, and you need about 1,000 of this to make one of that. Take note of that as well. So now, when you're asked to define solubility, what are you going to say? Solubility is the maximum amount of a substance that will dissolve in a given solvent at a specific temperature. We have to know that when it comes to solubility, we are doing it, we are finding our concentration at a specific temperature. So you need a temperature. All right. So we said solubility is the maximum amount of solute that will dissolve in a given solvent at a specific temperature. Form a saturated solution. So we need what? We need a maximum amount of solute that will dissolve in a specific or in a given solvent at a specific temperature to form a saturated solution. So let's look at the types of a solution. You have a solute and then a solvent. When you add your solute to the solvent, then you get your solution. So we have three types of solutions over here. So we have a solution that is unsaturated solution. We have saturated solution, and then we have super saturated solution. These are the types we have. So for an unsaturated solution, you can still dissolve more solute. But for a saturated solution, this solution cannot dissolve any more solute, and a supersaturated solution as well. And a supersaturated solution is very, very unstable. So this is where if you um, if you stir the mixture or you shake it a bit, they can create centers of nucleation can be formed, and this will cause um, this is going to cause precipitation. Okay, yeah, precipitation. So take note of that. Now, which factors affect solubility? So basically, solubility is just like how the extent to which something is going to dissolve in a given solvent. All right. So what kind of factors are going to affect solubility? We have temperature. So temperature is going to affect solubility. Pressure is also going to affect solubility. And let me say the nature of the solvent. So when it comes to temperature, temperature is going to affect solubility, especially for solids. Okay, so solubility increases as you increase temperature. Solubility generally increase as you increase temperature, especially for solids. When it comes to gases, it doesn't really work that way. And I'm using the word mostly increases because even for some solids, solubility doesn't increase as you increase temperature. So generally, solubility will sorry, for solids. When it comes to gases, gases are less soluble at higher temperatures. So gas pressure. So take note of that. When it comes to gases, they are less soluble at higher temperatures. So we are going to use the concept of like dissolves like, like dissolves like. So when you add maybe sodium chloride, you put it in water, it's going to what? Dissolve. Because this is polar, this is also polar. So it is going to dissolve. But if you add, yeah, so sodium chloride is soluble in water. But if you add something like kerosene to water, kerosene is not soluble in water because kerosene is non-polar, but then water is what? Polar. All right. So this is just this is just some basic definitions. So I want to move on to solubility curve. So as we stated, the unsaturated solution can dissolve more solute. Super saturated solutions cannot dissolve any more solute at a given temperature. If you plot a graph of solubility against temperature, you plot a graph of solubility against temperature, you are going to have three different regions. So let me say this is my graph. So you have region B and region C. So below the curve, you will have an unsaturated solution. On the curve, you are going to get what? A saturated solution. And above the curve, you are going to get what? Saturated solution. So take note of this graph. You can be asked to sketch this in your final exam. So now let's move on to the solubility rules. Then we quickly look at what we expect most. So these are some few solubility rules I want us to take note of. So let's look at the soluble salts. We are going to look at the ions of what? Soluble salts. So if we take the group 1 metals, they usually form soluble salts. Group 1 metal cations, they form soluble salts. So something like sodium, Li plus, sodium, Na plus, potassium is also there. So these are the group 1 metal ions. Okay, they form soluble salts. We also have to know that NH4 plus also form soluble salts. So all salts that are made up of these ions are going to be soluble. NO3 minus. All sorts of these ions are soluble. We also have CH3, COO minus. So no matter what, so all are what? Soluble. All are soluble, no exceptions. Then now there are going to be some few exceptions somewhere for Cl minus, Br minus, and I minus. These salts are soluble, but then we have some exceptions. So except mercury, when we see mercury together with any of these halides, it's going to be insoluble. We said these are soluble. We are looking at the soluble salts. If we see mercury, it's going to be what? Insoluble. If we see silver, it's going to be insoluble. And if we see lead, it's also going to be what? Insoluble. So this is what you used to know. Remember when I was doing a video on the halogens, the group 7 elements, fluorine, chlorine, bromine, iodine, and astatine. I said that FC Barcelona in Accra. And then you know that Messi used to play for Barcelona. All right. So this is how I kept it. All sorts of Cl minus, Br minus, and I minus are soluble except Messi lead. So this for mercury, this for silver, and this is for lead. Just a minute, I'll be back. All right, let's continue. So we've seen that we have one more SO42 minus sulfate. So this one too has exceptions. So the exceptions here are Ba2 plus, Ca2 plus, Pb2 plus, mercury is here again, and then we have strontium. So these solubility rules, you have to take note of them. Then now let's look at the insoluble salts. The insoluble salts. So for insoluble salts, phosphates as well are going to form. Now, how do you get the exceptions for these guys? Most of these ions will be cations. When they combine with these cations, they are going to form what? Soluble salts, because over here we said that any salt that is containing any of these ions will be soluble. Then we also have sparingly soluble salts also there. So they dissociate partially in aqueous medium. They are sparingly soluble. And one example is calcium hydroxide is sparingly soluble. We said hydroxides are insoluble, but then calcium hydroxide is what? Partially soluble or sparingly soluble. So these are the solubility rules. So let's check if some salts here are soluble or they are insoluble. Let's take silver nitrate, AgNO3. So will this be a soluble salt or it's not going, or it's going to be insoluble? So let's check. We can see this is made up of Ag plus and NO3 minus. And then we did say that all sorts of NO3 minus are soluble. So this salt is going to be soluble. Let's take potassium hydroxide, KOH. This is made up of K plus and OH minus. And we can see that all group 1 metal ions form soluble salts. So this is also going to be soluble. We are just applying our solubility rules over here. If we take calcium carbonate, this is made up of Ca2 plus and CO3 2 minus. And this is going to form insoluble salt, except when it meets any of these guys. And then calcium is not part of these guys. So this is going to form an insoluble salt. So this is insoluble. All right, so now that we've looked at this, a question can also be asked in this manner. You can be asked to determine whether a precipitate will be formed or not if you mix solutions of two salts. So let's say you mix a solution of this and this, zinc 2 chloride and sodium sulfate. You mix equal solutions of this, or you mix two solutions containing this and this. Are you going to form a precipitate or you're not going to form a precipitate? So right now, if you are going to get a combination that will give you an insoluble salt, then that insoluble salt is going to precipitate out of the solution. In other words, you are going to use what you call double replacement reaction. So you have AB plus CD going to, so now AD plus BC. Let me make it this way, CB rather. So this goes for that and this goes for that. Let's say we have A plus B minus C plus D minus, something like that. So the cation will go for the anion, and then this one will come for this, just like this. So over here we can have Zn2 plus Cl minus, and here we can have Na plus SO4 2 minus. So we can have this going for that. We count ZnSO4, and this coming for that. We have sodium chloride. So we have to apply our solubility rules now. All sorts of Na plus are soluble. So this will be what? Soluble. And then we have to apply this one too. We said that SO4 2 minus, they are all soluble. We gave some exceptions, and then zinc 2 was not part of the exception. So this one too is going to be soluble. So we will not form any precipitates over here. Okay, so now we can move on to the calculation aspects under solubility. Let's see how we can find or calculate for solubility products and ionic products. If you have something like this and put it in an aqueous medium, let's consider this as a sparingly soluble salt. We are preparing a saturated solution of a sparingly soluble salt. So this is going to dissociate this. This is aqueous, this is aqueous. Reaction, anytime you write a chemical reaction, you have to balance it. So A here comes X number of times, so we have to balance. Solubility is equal to X. Then we are going to use mole ratio. So this is, let me use S. We are going to use mole ratio. if the solubility of this sparingly soluble salt is S, then S is going to come here and S is going to come here. We are going to use mole ratio. So the number of times or the number of moles we have the ion for A must multiply our solubility. And when we get these two concentrations, our KSP is going to be equal to the concentration of this ion raised to the power x coefficient times the concentration of the other ion raised to the power x coefficient. So this must multiply this must multiply that, so that we get these concentrations, and we fix in those concentrations here. So until we solve an example, it will not make sense. So we'll solve an example quickly. So this is how you get KSP. But then if you are asked to find the ionic product, you just take the actual concentrations of what? These ions. And you do the same thing, you raise it to the power of their stoichiometric coefficients, just like KSP. But just that the kind of concentration you use for ionic products is different. That in ionic products, you're going to take the actual concentration of what? The ions to the power their stoichiometric coefficients. By KSP, you have to use the concentration you use for KSP is the solubility of the salt. Use the solubility of the salt for KSP calculation. But for ionic products, use the actual concentration in the solution. That's the difference between ionic product. And then you have to take note your ionic product. We'll solve questions right now, so everything will make sense. Your ionic product, QS. If your ionic product, okay, let me just write this. So they basically have the same expression. When you are doing the calculations, the kind of concentration you use is different. This one you are using what? Actual concentration. But here, we are using what? Uh, Let me say solubility. Exactly. Now, if your ionic product is less than your KSP, you are going to get an unsaturated solution. If your ionic product is equal to your KSP, you are going to get a saturated solution. But here, no precipitate will be formed. And if your ionic product is greater than your KSP, you are still going to get a saturated solution or a supersaturated solution, but then there will be a precipitate formed. So take note of this difference. This one too is very high yield, and it can come in your exams, or it will come. Let me put it that way. Okay, let's see. I got some questions here for you. Just a minute, so we start solving the questions together. Okay, so we have a question here. Okay, the image is not clear. I'm trying to fix it. All right, so let's take the first question. So exactly 0.11 milligram of silver bromide will dissolve in 1.00 liters of water. What is the value of KSP of silver bromide? And we are given the molar mass of silver bromide to be 187.77 gram per mole. So first of all, if you are calculating for KSP, you are going to use the solubility to calculate for the KSP. And when I began, I said the solubility can be expressed in terms of what? Molarity. Okay, the solubility can be expressed in terms of molarity or mass concentration. But when you just hear solubility, you are referring to general, referring to this one. But if you are asked to express solubility in mass concentration or in gram per liter, then you go for this. So obviously, we were given 0.11 milligram of the silver bromide, and it was dissolved in 1 liter of water. So this is going to give us mass concentration, because if you have mass over volume, you are getting density, isn't it? So mass concentration. But you can't use this mass concentration to calculate for KSP. You have to use the molarity. So first of all, we know the relationship between mass concentration and molarity. So that relationship will help us get the molarity. So let's get our mass concentration. So this is going to give us um, 0.113 milligrams. So the milli here, that was our brought it out, times 10 to the power minus 3. So all over, our volume is 1 liter, so all over 1.00. Then we can get our mass concentration. So 0.113 by 10 is basically going to give us the same thing, isn't it? So 0.113 by 10 to the power minus 3 gram per liter. Then after getting this, we have to get our molarity. So using rho equals MC, and we can get the molarity to be rho over M. So that gives us 0.113 by 10 to the power minus 3 all over. The molarity was given here, all over 187.77. So let's see what that will give us. So this is going to give us 6.018 by 10 to the power minus 7 mole per liter or molar. So we have our concentration in mole per liter. So that is going to be our solubility. Now we can calculate for the KSP of the salt. So we have to write our equation. So we are going to get Ag plus aqueous plus Br minus aqueous. If you don't bring the state, you will not be given the full marks. So now everything is balanced. We check and then it's balanced. So if our solubility is X, then the mole ratio of this to that is 1:1. So here is x, here is 2x. So our expression for KSP becomes concentration of Ag plus to the power 1 because the coefficient here is 1, multiplying concentration of Br minus to the power 1 because the coefficient here is 1. So we are going to get x by x. So our KSP equals x squared, and our x is the solubility which we calculated for over here. So basically, and then we are going to get 3.621 by 10 to the power minus 13. Because it was squared, this one had units of mole per liter, this one had mole per liter, so the unit becomes mole to the power 2, liter to the power minus 2. Or we could have replaced this by molar, then squared. So this is the KSP we calculated for. Okay, then we have another question. Write the value of the solubility product of the salt PB3 PO4 subscript 2 in terms of its solubility S. Yeah, and then we're given the solubility and we ask to calculate for the KSP. So we do the same thing we did at the top. So we prepare an aqueous solution of the salt. So this aqueous, this PO4 3 minus aqueous. Then we have to balance the equation. Lead came here 3 times, so this 3 and this is 2. The solubility was given as S, so the mole ratio is 1:3. So this will be 3S, this will be 2S. Now our KSP becomes concentration of the lead ions to the power 3. The stoichiometric coefficient is 3, multiplying concentration of the PO4 3 minus to the power 2 because the stoichiometric coefficient here is 2. So our KSP becomes the concentration of the lead ions is 3S, 3 times the solubility, so 3S to the power 3, multiplying this one was 2S to the power 2. So we are still solving the A. We are expressing the solubility products in terms of the solubility. So this becomes 9S cubed multiplying 4S squared. So our KSP becomes, so 9 by 4, that's going to give us 36. Then this one we are going to add the exponents. So these are expression for the KSP, and we can proceed to add the units. We know this is going to be mole to the power 5, then per liter to the power minus 5. Then now the solubility was given to us, and we are asked to calculate the KSP. So we just fix it in for the B. So this is for the A. So 36 into bracket 1.5 by 10 to the power minus 7, all to the power 5. So let's see what that will give us. So this will give us 2.73 by 10 to the power minus 33 mole to the power 5, then L to the power minus 5. So this is how we can calculate for solubility products. We've been able to solve the first two questions. The next two questions Okay, still under solubility product, followed by something I haven't explained. So I'll have to explain it. Okay, so let me explain that quickly, then we'll move on with the questions. So there's something called common ion effect. Yeah, there's something called common ion effect, and it basically uses Le Chatelier's principle, which says that if a system is under equilibrium and then a stress is introduced, the equilibrium position will shift in a direction which will nullify the stress. So let's say we have silver chloride, and we prepare a saturated solution of this, and then you you add Cl minus to this solution. So this is in a beaker. Okay, you prepare a saturated solution of silver chloride. Then you added more Cl minus. If you add more Cl minus, what is going to happen is that the concentration of what the Cl minus ion is going to increase. So if the concentration increase, remember initially this system was under equilibrium. The rate of the forward reaction was equal to the rate of the backward reaction. Now that you increase the concentration of this Cl minus, the equilibrium position must shift towards to this side so that it will reduce the total concentration of the Cl minus again. So that's basically what common ion effect is going to do. So you have the solubility in what of silver chloride in an aqueous medium in water. But then if you go and put silver chloride in HCl, if you go and put silver chloride in HCl, you will notice that the solubility of silver chloride in HCl will be different from the solubility of silver chloride in water because there is a common ion. Silver chloride contains the Cl minus ion. HCl is also containing the Cl minus ion. So this is what's called common ion effect. The effect is that since there is a common ion, they are going to increase the concentration of the Cl minus and the equilibrium position will shift backward to the left. So in effect, it will decrease the solubility. So common ion effect decreases solubility. And then let's see how we can do calculations on what common ion effect. So let's take the question 4. We have to compare the solubility of silver chloride in water and in 0.1 molar sodium chloride. And then, okay, let me make this HCl. Yeah, let me make this HCl. And they give us a KSP of silver chloride. So let's calculate the solubility of silver chloride in water. So in aqueous medium, we have silver chloride going to Ag plus aqueous plus Cl minus aqueous. And we know this is balanced. So if the solubility is X, mole ratio is 1:1, 1:1. So our KSP becomes concentration of Ag plus multiplying concentration of Cl minus all to the power 1 because the stoichiometric coefficients are 1 each. So we know KSP will be equal to X squared. So our X, which is our solubility, is square root of KSP. So the square root of the KSP was 1.8 by 10 to the power minus 10. Root of 1.8 by 10 to the power negative 10. So we have the solubility to be 1.34 by 10 to the power negative 5. This is the solubility in what? In water. I want to calculate the solubility in 0.01 molar HCl. So HCl, we know it's a strong acid, so it's going to dissociate completely and give us H plus ions and minus ions. So here 0.01, here to 0.01. Mole ratio 1:1, here to mole ratio 1:1, so 0.01. So already, so now when we put this in HCl, the silver chloride is still going to dissociate just like how it did in the first instance. The equations are balanced. Okay. Now, if we check, we know that our KSP will be equal to concentration of Ag plus multiplying concentration of Cl minus. But now the concentration of the Cl minus has been increased. We are adding an extra 0.01 molar, which means that if this one, our solubility, if our solubility here is still X, then mole ratio 1:1 here becomes X, but here becomes X plus 0.01 because there was already a concentration of 0.001 molar Cl minus before you added the silver chloride. So our KSP equals X multiplying X plus 0.01. But here we make an assumption that X plus 0.01 is approximately equal to 0.01. So our KSP is now equal to 0.01 times X. Then our X is KSP over 0.01. So our KSP was given to us already. So we're just going to divide by this. And so now we have our KSP to be equal to 1. Our solubility 1.8 by 10 to the power minus 8. So if you compare this and then you compare this, you realize that the solubility of the silver chloride in water is greater than the solubility of silver chloride in what? HCl. So in HCl minus, it has decreased what? The solubility of the silver chloride 1.8 by 10 to the power minus 8, and then 1.34 by 10 to the power minus 8. So this is much more smaller. So that is how you'll be tested on common ion issues. Okay, let's still proceed and solve this question, the third one. We've done a similar thing, but we can still do it again. Okay. So calomel, whose chemical name is mercury 2 chloride, was once used in medicine as a laxative and diuretic. It has a KSP equal to 1.3 by 10 to the power minus 8. What is the solubility of HgCl2 in grams per liter? So now we are asked to calculate for the solubility in grams per liter. We already established the fact that solubility can be expressed in mole per liter or gram per liter. When we just hear solubility, then we are talking about mole per liter. But when you are being asked, when it's being specific, or when we specify that gram per liter, then you express it as mass concentration. So since we are given the KSP, you can go ahead and easily find the solubility, which is in mole per liter. And then since you know the relationship between molarity and mass concentration, you can you can multiply your solubility by molar mass to get your mass concentration. That's the solubility in gram per liter. So let's go. We have our source HgCl2. So in aqueous medium, we are going to get what? Hg2 plus aqueous plus Cl minus aqueous. We have to equation first, isn't it? Mercury Cl2, Cl must be 2. So if the solubility is X, mole ratio 1 is to 1, so here's X, mole ratio 1 is to 2, so here's 2X. That's it. Ksp equals concentration of Ag2 plus multiplying Cl minus this to the power 1, stoichiometric coefficient, so to the power 2. So we have X multiplying 2X to the power 2. Yeah, so we just simplify this first. This gives us 4x squared. And finally, we get 4x cubed. So let's make x the subject, dividing through by 4 and taking cubic roots of both sides. We get this. So we can easily get our solubility. We know that the KSP was given by 1.3 by 10 to the power minus 18. So all over 4. So cube root of, we have a fraction 1.3 by 10 to the power negative 18. And the denominator is 4. We are getting 6.88 by 10 to the power minus 7 mole per liter. But then we are asked to find the solubility in grams per liter. That's mass concentration, or what you know as density. So we know rho equals mc. So we can easily find that molar mass was given to us already. So it's just 472.086 by 6.88 by 10 to the power minus 7. So the solubility we found, we just multiply by the molar 472.086. And then we are going to get 3.25 by 10 to the power minus 4 per liter. So this is it. This is what we have. Okay, so we've been able to solve the first 4 questions. And we have question 5, 6, 7, 8, 9 waiting for us. So let's cover more concepts, then we can solve the subsequent questions. Okay, we can solve question 5 and 6 because we've done, I explained ionic products as well. Cool. Okay, let's do one more calculation on solubility first. So we want to calculate the solubility of magnesium hydroxide in water, and the KSP was given to us. So there's no need to delay with this. We just write that we are going to get Mg2 plus OH minus, or aqueous. Then we have to balance magnesium 1, OH2. So we have to bring 2 here. If the solubility is X, 1 is to 1, 1 is to 2. So we have X, we have 2X. Ksp equals concentration of Mg2 plus the power 1. Stoichiometric coefficient is 1. Multiplying concentration of OH minus to the power 2. Stoichiometric coefficient is 2. Ksp equals, so we have X multiplying 2x to the power 2. Ksp equals X multiplying 4x squared. Ksp equals 4x cubed. Yeah, so we can still do the same thing with it. Cubic root of Ksp, which is 8.9 by 10 to the power minus 12 all over 4. So now we have 8.9 by 10 to the power minus 12 all over 4 cubic roots. So 1.31 by 10 to the power minus 4 mole per liter. So we've done this. Now, questions on ionic products and solubility products. We want to predict whether a precipitate will be formed or not. So this is question 9. Sorry I skipped 5 and 6, but from here we'll solve 5 and 6 and 7. Oh, there must be a question 10. Okay, there's no question 10. In a saturated solution of hydrogen sulfide, the concentration of sulfide ion is found to be 8.0 by 10 to the power minus 21 molar. If Fe2 plus concentration is 0.01 and Cu2 plus concentration of 0.01 are added to the sulfide solution, deduce whether FeS and or Cus will be precipitated. So this is a replacement reaction, right? Or precipitation reaction. So let's check. Since we are given the concentrations of these ions, we have to find the ionic product. First of all, we're given the KSP. Are we given KSP? Okay, we're given the concentration of the sulfide ion to be this. Okay, so now we have to find the KSP. Or we need the KSP of H2S so that when we find the ionic product, we can compare to the KSP. All right. So let's check something. Since we don't have the KSP of the H2S, then let's find the KSP on our own. But before that, let's solve this one first. We'll get back to that one. Let's take question 5. One form of kidney stones in calcium phosphate, which has a KSP of this. So you see here we've been given the KSP of calcium phosphate. A sample of urine contains 1 by 10 to the power minus 3 calcium molar calcium ions and 1.0 by 10 to the power minus 8 molar phosphate ions. We are to calculate the ionic product or reaction quotient for it and predict whether the calcium phosphate will precipitate or not. So we just go ahead. We are going to get Ca2 plus aqueous plus PO4 3 minus aqueous. Then we balance. This one comes twice. Since we are given the concentration of the ions, we can find the ionic product. So our ionic product equals concentration of Ca2 plus raised to the power 3, concentration of PO4 3 minus raised to the power 2. Remember I told you that it has the same expression as the KSP expression, but just that for KSP expression, what you are using, the concentrations you are using is your solubility with respect to their mole ratios. But here you are just using the actual concentrations given to you. That's why it's called ionic product. You're using the actual concentration of the ions. So your ionic product is going to be, we're given the concentration of calcium and concentration of the phosphorus is 0.0 by 10 to the power minus 3 to the power 3, multiplying 1.0 by 10 to the power minus 8 to the power 2. Robert, find the concentration of AU that's precipitated. So now concentration of AU plus remaining in the solution is 1.11 by 10 to the power minus 5 molar. Okay, and the concentration of AU plus ions initially was what 0.01 was 0.010 molar. So now we have to get the concentration of AU plus that precipitated. So that's going to be 0.010 minus 1.11 by 10 to the power minus 5. And this is going to be, so let's see, minus, we are getting 9.99 by 10 to the power minus 3 molar. So we can then go ahead and calculate the percentage of what? AU plus that's precipitated to be equal to 9.99 by 10 to the power minus 3 over 0.010 by 100%. We're going to get 99.9%. So basically, this is what this is what you expect for your Chem 113 exams. You get a question on fractional precipitation, and you can be asked to do the most basic calculations here, or they can proceed to ask you this to calculate the percentage of a particular ion that's precipitated before another one began to precipitate. So take note of question on what fractional precipitation. So these are the high yield areas that we expect for your Chem 113 exam, and we've covered them. So fractional precipitation. How to calculate solubility product. How to calculate ionic product. So these basic things. Yeah, and then common ion effect. So these are the high yield areas, and then we covered all of them today. Thank you for joining the session. God willing, tomorrow we'll do redox reactions. Good night.